on Thursday, finally got all the details, so I'm confident to share Hopf invariants for fundamental groups. Remember, Hopf invariants were for higher homotopy groups, but this is for pi1, just a wedge of one spheres, but I think that's a pretty good start, actually. It was not so easy even in that case. And the Harris paper on bot periodicity, I had a couple of folks ask, and in case you can't get it yourself, I'll post it. I've been meaning to, so this announcement is as much as anything a reminder to myself. And then I wanted to, let me do one thing. Let me set out a mark for later where I'll try to restart. And I wanted to then discuss an erratum. So that's, and this was pointed out by, let me do one other thing, which is make this a little bit smaller. This was pointed out by Andrea Bianchi, who's now in Bonn. Namely, so last week we talked about characteristic classes. I tried to give sort of very direct geometric definitions through submanifolds of the total space of the bundle. So if you've got a base which is a manifold, then the total space is a manifold. But and that of course works for the Euler class, but if inside of the direct sum, I think about the collection of things in a fiber which are linearly dependent, maybe we'll call these things lambdas. This will not generally be not a smooth manifold. So it is what it is you've got it's a cone on its intersection with the on the locus on the unit sphere, at least for say the direct sum of two rank 2 bundles. And so, yeah, so I wanted to just mention some ways, some possible fixes. And I don't have a strong preference here. Well, I'll tell you what, I've got a preference, but not a super strong preference, because frankly, I haven't worked it out. So possible fixes. Would be, well, if you follow Whitney, you can pass to the sphere bundle. And that's where he was working, and it's not so easy actually. But notice that you're not really working in the base effectively, and you have a big question about whether if you're going to play these games between the base and the total space, I don't know how to guarantee sections like in the vector bundle themselves, which is kind of nice to go back and forth between the geometry of the bundle and cohomology of the base. So you could also just sort of work around the singularities. So, and in general, this would be for Tome classes of codimension 2 or greater. And the idea being that if I just have an F, in this case it was in total degree n-1, this was the n-1st Stiefel-Whitney class from E plus E. And we're assuming it's transverse to lambda, but if we also assume that it's transverse to 0 plus 0, which is the point that this is the cone on. So this is, let me go back here. This is cone sort of 2, 0, plus 0. Anytime you have that linear dependence, I can scale all the vectors involved, and that includes down to 0. But this would mean that it's that the preimage of this is empty. So even though you don't have a sort of submanifold in general, this pair of conditions would mean that you've got a 0 submanifold nonetheless. And you would also need this, why codimension 2, you need this for homotopy, actually what I should say is just anything of the next degree to get the coboundary of a cochain. But again, the preimage of the singularities would be empty. So one would have to modify the definitions to include objects with high enough codimension singularities. And then the final proposal, these are all just proposals. And again, I haven't worked this out because it's just not a priority with all the other things I'm trying to figure out, is you can define Tome cochains. They're already defined for immersions if you want, but for other proper co-oriented, so there'll be some sort of vector bundle around maps. And again, extending from the definition for immersions. And this is basically follow Quillen's treatment of complex cobordism. So bordism has a manifold definition, but so does cobordism. So Quillen did this in this paper, Elementary Proofs of Some Results in Cobordism Theory. So, so those are some thoughts. Be happy to discuss with people if they had a reason to want to further develop things rigorously. Could these classes be the Tome classes of the 0 section of alternating power bundles? Oh, I don't know. Maybe. So let's let everybody ponder that, and let me continue on. But that's a great idea too. Right? Could they be the 0 section in something? Right. Oh yeah. That would seem like it would do it, wouldn't it? Okay. So let me let me go ahead and that would be a nice or Near's suggestion. Replace E plus E by lambda squared E, right? And then play the 0 section game. Play the same game with zero section. Although that's, all right, now I'm a little skeptical. The codimension of that bundle is not n-1, but maybe, or something. Okay, let me sort of say why, at least philosophically, one would want to resolve this somehow. Because again, it's not easy to prove the Whitney sum formula, for example, and prove that these classes exist. That essentially comes down to proving the Whitney sum formula. And and again, the Milner and Stasheff approach was to appeal to the definition of Steenrod operations, but Quillen in particular, in this paper that I cited, and others, it actually advocates for going the other way around. So let me talk about the Tome cochain dictionary, which is one topic that I wanted to do at the end of the last lecture, and it'll feed into what we're going to do today. So the payoff could be the last bit of this Tome cochain dictionary, namely. So let's sort of review what we have. So on the one hand, we're looking at submanifolds, and again, they can be immersed actually, or I usually like to at least develop them with corners, and we get cochains from them. One thing you can do is once you allow boundary or corners, you can take the boundary. And I argued in the sort of catch-up lecture that yields co-boundary. If you take union, that means sum. And of course, once you have the boundary co-boundary, that means that if you happen to find a nice closed submanifold, you've got a cohomology class. Now, there's a big question about whether you can always do it with such, or you have to, again, as we just showed, you might need to go to some things with singularities, or you know, by allowing things with boundary and corners, you could actually sort of piece things together. But again, we can just imagine at least sometimes we represent things by honest submanifolds. And then if we pull back under a transverse map, that is just the induced map on cochains. On the other hand, if we take the image of something under a proper map, then that's all of these games with usually often sort of just formally given by Poincare duality of these Schriek maps. And the way we've constructed them, it's through these that you can view suspension isomorphisms, or more generally, Tome isomorphisms, as I discussed last time. And then if we do intersection, and I hope to come back at this, it might be a few weeks on, because I want to do some group cohomology first. And again, we're assuming some transversality here. Then that's cut product. And I'll preview, you know, plus there's actually non-zero co-boundary if you want cut product. It's also wedge product if you're doing Duram theory, and that you can more or less arrange to be true on the nose. But then finally, if I've got a submanifold and I look at the normal bundle, because that is a piece of data, a God-given piece of data, as Bott would maybe say, then what does the having a normal bundle mean? Well, you could maybe take characteristic classes of those. This is again just for the closed submanifolds, or the ones that you have the normal bundle. Other ones you would have to feel, you'd have to modify for the technical variant that you were working on. And in any case, those characteristic classes correspond to Steenrod operations. So again, in the spirit of what we're doing here, this is sort of a geometric view of Steenrod operations of submanifolds cohomology through intersection. Then, well, a submanifold has a normal bundle. We learned that in differential topology. That's some data, and that gets reflected in these high-powered cohomology operations. So let me make that a little bit more precise, namely the Wu formula. Which says that if W is a submanifold, and then nu is its normal bundle, then the way I'm going to put it is, if I look at the Stiefel-Whitney classes of the normal bundle, and then I look at the induced map. So that's really, if I'm thinking of these Stiefel-Whitney classes as represented by submanifolds of W, well, a submanifold of W is a submanifold of M, and so that also yields a Tome cochain, Tome cocycle. Well, that's just square I. That cohomology class is square I on the cohomology class represented by tau W. So yeah, so this is sort of well known and goes back, and again, sometimes you can take this as a definition of the left-hand side, but geometrically I really think of it more as almost a definition on the right-hand side. Okay, well, let's so that's sort of something picked up from last time. Let me oops, oh, shoot. Let me now start on the next board and sorry for technical difficulties. Somehow things, oh, it won't be the next board on link to, sorry, the next board as in where I set out in this board. Okay, there we go. Let me do the same thing here. There we go. So let's talk now about our main thing today, which are Eilenberg-MacLane spaces. So let's, and I'm gonna emphasize the iterated bar model. This is a model for KZ2N, and we can get our own version which fits on our desk if we allow the points to be animated and move around by just, because this is Z mod 2, every point there is the non-trivial element of Z mod 2. If two of them collide, they vanish. If any of them wanders off the edge of the box, they also vanish. And then the next thing I want to recall, because I don't think everybody in this series knows this fact, so recall, in quotes, I'll be brief, that these represent cohomology. So if I take maps from X into this space, that ends up being, well, the right-hand side is a group because these are topological abelian groups because, well, that's the model that we chose and that allowed us to iterate the bar construction. So the right-hand side is a group, and I can take some F to F upper star of a class we'll discuss in a moment that exists in in degree n, you could just say it's, there's a Hurewicz theorem that applies. So we know that the nth homology is Z mod 2, and therefore the nth cohomology with mod 2 coefficients is Z mod 2. But again, we're going to talk about the geometry of some of these classes. And then, so this is a natural transformation between functors. And then you show that the latter satisfies the axioms for cohomology, especially the key one, the suspension isomorphism. And why is that? Well, we have that if I take maps from, so the n plus first cohomology of X, suspension of X should be the nth cohomology of X. Well, by standard adjointness, maps from a suspension, if I take the suspension coordinate, instead of thinking of this is maps from pairs X comma T, then for every X, I've got a map from the interval. And I get this as loops, okay, Z mod 2 n plus 1. And then I claim this is going to be then X into K Z mod 2 n, because in general, loops BG is equivalent to G, and we can show that just by, let's see. Yes, thank you. I should say reduced cohomology. Thank you, Andy. I might, yeah, I might neglect that at times. So, so why is this last one true? Well, there's again just a little comparison. So loops BG sits in a fiber sequence with paths on BG and BG. I can map paths on EG to that and BG there, and then I would get some fiber which is equivalent. But this also then maps to EG, which has its quotient to BG there, and this of course has fiber G, and so we have this this equivalence between loops BG and G. Great, and in general, the right. By the way, let me make a remark. If M is a monoid, then BM exists, and loops BM is defined as the group completion in algebraic topology and homotopy theory. So it differs from what you might normally think of as well, if you think about the construction of the integers from the natural numbers using pairs of things in M, but it's the right group completion for purposes in algebraic topology. So I wanted to then, so these are our spaces, these Eilenberg-MacLane spaces. They represent cohomology, and what this means then is, well, if I've got a map from K, Z, N, sorry, Z2N to K, Z, to M, that of course acts can be composed with x into k z2 in to give cohomology operations. And so, the cohomology of Eilenberg-MacLane spaces themselves, this is akin to, for example, let me write that. So this is akin to representations of, you know, however you want to say it, GLN, act on the set of representations of G, because if I've got a homomorphism from G to GLN, and then I've got some other homomorphism from GLN to GLM, then I've got some new representation, and things like exterior powers, as we were discussing, fall into this category. We won't digress, but this is entirely this kind of, you know, categorical. Once you have a representing object, you can look at its automorphisms, and that gives you operations. And then let's recall the theorem, and I'm not going to prove this this time for sure, but I just want to, by way of contrast of what we're going to get at, the cohomology of k z2n mod 2 is actually a polynomial ring on classes that are these basic Steenrod operations composed on the fundamental class, where as I ranges over admissible operations, and I haven't defined these, and again, this is just for kind of contrast with what we'll be doing. So these are admissible sequences of excess less than or equal to n. And this is the standard treatment, is a spectral sequence argument of Borel, although I don't know if that's the original argument, but you can use a Leray-Serre spectral sequence to, iteratively. It's quite a technical technical tour de force, actually, to get that. So again, the iota n is a generator, the non-zero of h in kz2 n with z2 coefficients. The fact that there is such, you standardly allude to, as I said, the Hurewicz theorem and universal coefficient theorems to know that there is such. But there is a good question: what is that class? You know, is there something? Can we feel like we know that class in a more tangible way? So now let me switch whiteboards, because let me now go over here. So, so today I'm going to focus instead on homology. And let me also get the scale right. On homology, which is not something you see treated nearly as well, but and then let's use some structure that is present. We'll use actually two pieces of additional structure, which will help us. And let me already say now that let me admit and put it in black and white. I don't understand everything, or even as much as I'd like, about about the whole story together. That is the homology and the cohomology and all these structures. So I'm going to share some structure and homology that's not even reflected in that standard statement. All right, so let's take it slow. So for each n, each of these, which again, I'll emphasize the model I want to think about, but this is another name for kz mod 2n. This is a topological abelian group. And that's going to imply that the homology is a Hopf algebra, is a commutative and co-commutative Hopf algebra. Okay, this is why Hopf created Hopf algebras, because if you have a multiplication on the space, then, and like for example, a Lie group, then you get a multiplication on homology. So, so again, the multiplication comes from the multiplication on the group. The co-multiplication is, well, homology always has a co-multiplication. You can think of it as dual to the cup product, but really it's also any space has a diagonal. So, and then everything in the world is compatible. It's a group, so you actually have the antipode as well, not just a bialgebra. But what folks might not realize, even who are familiar with this, is in this model. So for R a ring, there are lovely maps, Bn R cross Bm R, and Z mod 2 is certainly a ring, to Bn plus M R. And of course, I'll draw it in the only dimension I can, namely in m equals 1. So I've got a couple ring elements here, and then a couple ring elements here. And what I can do is take the product of cubes and then multiply, sort of as you see, both in the Cartesian product. That's R2. And you've got other products here. So that's an explicit ring structure, multiplication on the union of these d-loopings of R. And the, these endow the homology of the union, which I'll think of as the direct sum, as maps from, well, the first thing is these are familiar. Now this object that we're representing is a ring, because if I have some f, let's see, if I have some f from x to BNR and g from x to BMR, I can just take the product use this clever multiplication, and then precompose with the diagonal, and I get a multiplication on, I get a map from x to bn plus m. And then, right, then a key proposition is that this coincides with the cut product. Actually, don't know, maybe the experts around can let me know what their favorite proof is if they've got a quick thing to say in the chat. I don't have a proof that I can rattle off. Okay, so you've got these multiplication maps. So then the point is, then we're looking at the homology of this collection, the cohomology being cohomology operations. But now let's just think about the homology of these representing objects. And then, you know, the proposition for the proposition is that the homology of, the homology of these forms, and you would want some sort of at least some kind of field coefficients. So if you want, you can think of this as a ring and this is some field, but this is what's called a Hopf ring. So what do we mean by that? Well, Hopf algebra is a group object in coalgebras. So an object for which when you map into it, you've got a group structure. If you want, bialgebra is a monoid object in the category of coalgebras. And so Hopf ring is a ring object in coalgebras. And really, I think we should just call Hopf algebra Hopf group, and bialgebra should be a Hopf monoid, and then everything would be consistent, but there's no way to travel back in time and enforce such things. But I should have probably put those in color because that's not standard. So what does that mean? That means I've got two products I've got a product coming from the additive product. And in this case, it's going to really only be defined on the homology of each direct summand. It's going to be 0 between them. And I've got a product coming from the multiplication. And they're both form a bialgebra. The plus product, if I actually have a Hopf ring, has an antipode. So let me just, I'm talking, but I'm not writing out everything just because it's a little bit tedious. And then the fun thing is that the plus product, the times product distributes over the plus product, because distributivity again was true at the level of the original multiplications, which by the way, just immediate geometry is establishes it for the Eilenberg-MacLane spaces. Well, this is equal to, I'm going to take the sum over the coproduct of A is some A I tensor A prime I, or I'll call them alpha and alpha prime. And then you take alpha prime, alpha I times the B, and then the alpha I primes times the C's. So you have distributivity of the times product over the plus product, but it uses the coproduct. Okay, so that's a lot of uh, uh, structure. And then now let me give the nice little theorem due to Steve Wilson. I want to say, maybe others, he doesn't necessarily take credit, but he certainly gets some credit for popularizing this. I would give him credit because actually it's, so the homology, the mod 2 homology of Eilenberg-MacLane spaces is the free Hopf ring over the single ring, which is the homology of the very first one. So if we know what this is, and I'll tell you what that is in a moment, then somehow everything else is sort of given by this structure. So, so yeah, this is, I think, a really lovely statement and worthy of knowing better. So let me move up again. Let's see, there's a question. How does this theorem relate to the Dwyer-Lashoff or Dyer-Lashoff operations? Oh, so right, over the Hopf algebra, let's see. Did I not say that right? Well, I didn't say over, right. Andy, it's not over the Hopf algebra, given by that homology. So you want both the coalgebra, but you want to extend the ring structure on that. It will become clear. And then there's a question: how does this relate to Dyer-Lashoff operations? That's a great question, Igor, and I'm going to come back to that after talking about some cohomology of symmetric groups. So absolutely, that's essentially, as I was saying, I don't understand as much about that as I'd like, much about this as I'd like, and in particular, the question you bring up, what is the relation between this homology and Dyer-Lashoff operations is a great question. I'm getting another question. So Hopf ring is a ring in Hopf algebras. No, Hopf ring is a ring in coalgebras. So there's two products and one coproduct. All right, I was putting all the structure out there. Let me get to sort of actually unpacking what Wilson's theorem says. Okay. Sorry. Okay. Great. So let's just start simple. Let's just start with the homology of BZ2, which is RP infinity. This is a Hopf algebra. And the standard way to treat that is that this is dual to the cohomology, because we're just doing, and I'm gonna, we're just gonna, oh, Andy has a good point that we need when you need the group ring of, or the ring of that, do you also need the, yeah, those are the unit classes, probably. All right, we'll clarify those. This homology is, of course, dual to the cohomology. We all know what the cohomology of RP infinity is. By the way, the right way to treat that is through intersections, right? We want to think about RP codimension I and RP codimension J for RPV and RPW intersecting in the intersection of V plus W. And so this is also a Hopf algebra, and that's polynomial, generated in degree 1, and thus primitively generated. And so that implies by results of Milner-Moore, if not older, that it's that the homology is divided powers. And I will give a definition for what that is. But again, I'm just paying homage to the standard treatment. But geometrically, the multiplication, which remember is coming just from plus, I'm only going to think of that alone right now. Is cellular, actually. And so we can just compute it directly. So let's recall that, so yi be the non-zero class in hi. There's this cell with, we've got I non-zero points. And then what I can do is, let me just give an example. What is the picture of y2 multiplied by y3? Well, I'll use color. I got, say, 2 points, and then I've got 3 points. And all of these are supposed to range over all possibilities, but then when I multiply them, it's just take union. And you see that, that of course, generically, I get 5 points. But not every point here, well, but every point here is actually the image multiple times of things in the factors in the product. And so what I get is that this is equal to, in this case, it would be 5 choose 2 or 5 choose 3 times that, because every point here is covered exactly by whatever choices I have of red and blue. But this would also be the image of any other red and blue coloring of those 5 points. So this ends up being cellular, and if you're calculating in cellular homology, then you get this, this is y5. So in general, you get, so this is the definition of divided powers, that you've got a sequence of generators, and yi star plus yj is I plus j, choose I, yi plus j. So that's divided powers. These numbers, of course, we're doing mod 2 homology. So at p equals 4, or not at p, but just if I'm working over z mod 2, this means that I'm exterior over things in degrees which are 2 powers. Oh, let's see what I, oops. So in this case, the coalgebra structure on homology. So the coalgebra structure on homology is coming from the cup product. And then the algebra structure on homology is the sum on the ring product. So we get two algebra structures around. If I just pick a single Eilenberg-MacLane space, there's one algebra structure, and namely it's coming from the plus product. And I haven't talked about the multiplication product yet. So why is this? Again, this would be that for example, so y3 is going to be is just y2 star plus y1, because even though there is a coefficient, it's 3 choose 1, which is 1. So I don't need y3 as a generator, whereas, for example, y4 is not a non-trivial star product. And then any one of these, again, there's a little binomial coefficient that you can calculate to say that they annihilate themselves. So we get an exterior algebra at the prime 2 as our divided powers algebra. Okay, so let's now go over to n equals 2. N equals 2. So again, I might need, let's see, right. Let's just think about reduced homology for the moment. The first thing to consider would actually be y1 star times y1, looking at Wilson's theorem. And this says that I've got a class which, so in the definition, if I've got two things here, then the product will be a point there. So there's an obvious two spheres worth of points. So this is represented by a map from S2 to B2 Z mod 2, taking the point in the square. So this is square modulo its boundary, taking a point in the square to this kind of configuration, if you will, with just exactly one point in this iterated bar construction on Z mod 2 at that same place in the square, and then those vary over, over all possible points in the square. And this is dual to this iota 2 in H upper 2. So this is kind of a fundamental class, sometimes people call, because it's the one that you're applying Steenrod operations to. And there it is geometrically in general. So let me just say in general, y1 star plus to the n times is going to be dual to this iota n. So there's always this in-dimensional homology class. It's the bottom homology class in reduced homology. And it's sort of given by a single point. If I'm thinking of configurations, a single point configuration labeled by the non-trivial element in Z mod 2, taking on all possible positions in the cube. So that's the very basic one. Next thing you would look at is y1 star times y2. So that ends up being pairs of points which are on a line here. So this is my y1 up here and my y2 here, and then the product. So if you think about it, this is a three-dimensional class because I specify the line, that's 1 degree of freedom, and then the 2 points on the line. And then you would, for example, have y1 star times y3. Well, again, just to let's see. So this is equal to y1 star times of, we're at the prime 2, so y1 star plus y2. And this is, so this is equal to the sum over, I've got to take the coproduct of y1, but that's just y1 tensor the unit, or I could also call that y0 plus 1 tensor y1. So there's only going to be two terms. And when I multiply them, so the first one would be y1 star y1, and that's my star plus, or sorry, that's my star times star plus 1 star times y2, and then plus the reverse, y1 star times y1 star plus y1 star times y2. And then what are these? Well, I didn't say, but 1 star one star anything is 0. Somehow I was expecting this to be something else. Sorry, I just realized I might have made an error in. I think now I've got it correct. I guess I misdid the coproduct in the notes. Geometrically, again, it's pretty clear that what we want here, let me draw the picture. I guess I'm just, you would have things like this. But I guess that's 0, actually. Let me say that y2 star times y2 is non-zero. It's some class that involves 4 points. But if you think about it, they're the vertices of a square. So really only 2 of the points matter. Pick opposite 2 or something like that. And so, right. And so if you, and you're looking at all possible arrangements, yeah, I'm getting a little tongue-tied at the very end of the lecture today. I claim that this is the equal to the class if I just forget about 2 of the points. But for every square, I can have a bottom left and upper right. And because I don't have the same multiplicities as I did when I'm doing the star plus, the space of squares occurs exactly once uniquely for every point in the image of y2 star times y2. And that space of squares is the same as the subspace of configurations of 2 points. So we get this class in degree 4. Right. So my apologies about one of those products not being up to snuff. But otherwise, this gives you an idea of just sort of this Hopf-ring statement is very geometric, and you get sort of pictures of all of the homology of Eilenberg-MacLane spaces. And again, let me talk and start. There's plenty here that I don't know. I feel like I don't know as much as I know in this area in particular. You know, and I'll say this again, but what is the relationship to, i.e. the pairing with, the standard cohomology statement? I feel like that would be nice to be clearer. And also, so far I've given you two statements, and I alluded to the proof being well known in the cohomology setting, and I'm assuming that's sort of what Wilson didn't give a proof in his notes in the homology setting. But is there a more elementary geometric proof of both statements using homology and cohomology together? So the homology is more geometric. Cohomology has a composition, so there's another structure that we aren't seeing on the homology side, and a couple structures we used on the homology side that aren't usually used on the cohomology side. Can we put those structures together sensibly and understand the homology and cohomology, this very, very basic calculation, more thoroughly? So I'll stop there. I'll come back to some of these ideas after we talk about cohomology of symmetric groups, which is actually where I've developed related things more thoroughly. Although it's again going to be more questions than answers, I'm afraid. Okay, we'll open it up to questions in the chat or otherwise, and then let's see. Right, so just a private message. Any questions about this?
Can I make a couple of comments on what you said? I think it's very interesting. My personal feeling is that there are two issues that are lurking around here. One is that, as far as I'm aware, nobody has ever really thought about the kind of questions you're saying from the point of view of what you might think of as E-infinity ring spectra. If you take an E-infinity ring spectrum and take the omega spectrum as a collection of spaces, you have an operatic structure. And if you hit that structure with homology, you should get a Hopf ring, but you also get a lot more structure that's not in this setting.
Mm-hmm. Yes.
And I think a lot of the questions you're asking really need that to be properly, because
right.
Ring, you know, where you're taking the cut product, you want something that kind of distributes over the additive structure, as well as, you know, being a sort of multiplicative structure. So in order to encode all of that really properly,
right.
I need to disassemble what is something like an E-infinity ring spectrum. And I don't think the language of Hopf algebras was ever set up to formalize that structure. The other point is, I think there's another subtle point that you notice when you look at all of the calculations in the literature, which includes the one you're talking about. They all basically prove the Hopf ring associated to the spaces of an omega spectrum, of an omega ring spectrum, is some sort of algebraic gadget, which turns out to be a free gadget, right?
Mm-hmm, mm-hmm.
In all the examples, you notice something very interesting going on that's not part of the axiomatic structure of a Hopf ring, namely the suspension map. right?
Mhm.
If you look carefully, all the calculations at some point prove, for example, the MU one, you prove that the square of the suspension coincides with something else, right? The multiplication by 1 in the second space or something. And that's not part of the structure that they formalize. And that is
Right,
actually
right.
there when you talk about a spectrum. So I think there's a whole bunch of questions which are very much related to what you're saying that need sorting out. And I'm not aware that this has ever been done properly.
Yeah.
I mean, maybe this is something along the lines of what you're thinking about, but it's something that's always bugged me about this structure. Of course, I mean, the Eilenberg-MacLane case is a sort of first case, but the MU case or the MO case, those are the kinds of examples that were done originally.
Right, right. Well,
And
yeah. Yeah, I would fully agree. I mean, one thing about this is that, right now we have these products, but in the 2020s, we know that everything we should think about as in derived algebra. So absolutely.
Yeah.
And I do think that would clarify some of this. But there's also, I think, some very basic combinatorics here that, you know, this is something that pairs with the Steenrod algebra. Well, up to, I mean, there's this free algebra on the Steenrod algebra. Basically, it's you kind of blur things a bit, and it pairs with the Steenrod algebra. What is its relationship to the Milnor dual? Is it the same? I'm not sure, actually. Is it a different kind of dual? What, you know, there's...
So, sorry, can you repeat that last sentence? What?
So,
to the...
let me put it this way. So the cohomology of KZ mod 2n is this polynomial algebra on a piece of the Steenrod algebra.
Yeah.
So I mean, if we let n be big enough, we see as much of the Steenrod algebra as we want.
Yeah.
Therefore, the homology, I guess we could say, is the co-free commutative co-algebra on the dual of that piece of the Steenrod algebra. This is just pure linear duality, right? And therefore, yeah, so therefore this is, there's some change of basis, or more basically a pairing between the classes. Maybe I should have just said it that way. You know, I can take some Hopf ring expression in these yi's now. So y57 star times y22 star times something else. That's some combinatorial data. And then I've got on the Steenrod side, I can then take my favorite Steenrod operation and ask, okay, what's the homology cohomology pairing? And so that's a sort of a very concrete question, which I suspect actually somehow the structures that you're talking about might be a part of that that answer. In other words, these structures are sort of kind of universal free in some way that then determines that pairing.
Well, I think you're right, and you know, the viewpoint I was thinking about was you should certainly think of homology and cohomology as defined over the Steenrod algebra. But if you do it properly with the whole infinity operatic structure, you get something which is going to come with a Dirichlet structure as well. And if you look in Ravenel and Wilson, for example, the MU calculation, there's a very, very brief discussion of Dirichlet operations for the structure. In fact, the multiplicative Dirichlet operations for MU work much more simply than the additive structure. They give a sort of slightly hand-wavy discussion of the additive Dirichlet operations.
And in this case, the additive ones would be 0, of course, because these are
well, exactly, yes, but the multiplicative ones are not quite trivial.
Yeah, no, they aren't. I mean, you've got these reflections of the sphere. So for everybody else who's
Sorry.
I'll
Yeah.
try to get back to some of these ideas after we do some homology and cohomology
Yeah.
of symmetric groups, by the way. So please don't feel like we're having this conversation between friends and you're never going to sort of
Sorry.
hear about this again. Let me ask for any other questions, public questions, and then I'll stop the share. All right, I'll stop sharing. If there was any, let's see. What I really wanted to do is stop the stream. I'm not seeing that. Let's see.